first place.
Yeah,
and because
absolutely.
we are not able to specify that, we simply try something, you see? So you could also focus more on what actually would be a good thing to develop.
Yes, yes, absolutely.
Okay, I guess it's about the time. We probably need to move on. I'm pretty sure this is a very, very hot topic. So, and if you want to engage with the discussion, we can do this in our session later. Okay, so we now have to move to the sessions, which we have a few contribution talk. So yeah, the first one, seeing you. So are you ready?
Yeah.
Okay, so if you can share your screen.
Okay, so hopefully you can see my screen and hear my voice clearly.
Yeah, please keep your time.
Okay, I will try. Okay, so yes, my name is Xingyu. I'm currently with the Computer Science Department at University of Liverpool. Today it's my great pleasure to present our paper called Assessing the Reliability of Deep Learning Classifiers through Robustness Evaluation and Operational Profiles. And this is a joint work with my colleagues from Hernández-Orallo and UK Disto. So first of all, I would like to mention what exactly our work is about. So our work essentially is about building a reliability assessment model for deep learning classifiers. And to the best of our knowledge, our reliability model is the first one that explicitly considers the operational profile information and the robustness evidence. And you may wonder, why we should care about this operational profile and why we should care about this robustness evidence in reliability assessment. So because first, software reliability by definition is a user-centric property. And yes, the reliability is essentially depends on how the users operate the software, and the operational profiles models the end user's behavior. And second, it's kind of well known that deep learning models are having unrobustness issues. So to us, any assessment model on deep learning without considering robustness evidence is not quite convincing. And the output of our reliability assessment model are some reliability claims on this metric PMI, which stands for the probability of misclassification per random input, normally like images, right? And the exact form of the output could be some confidence bond or mean or variance on this PMI metric. So specifically in this paper, when we try to assess the delivered software reliability, we use this PMI probabilistic metric defined in equation 1. And this equation 1 intuitively says, if I randomly select an input X according to this function OP, stands for operational profile that's modeling the end user's behavior, what's the probability that this X will cause a misclassification? And for deep learning robustness, I normally write robustness requires the decision of the deep learning model should be invariant against the small perturbations on the input. And for sure, there are many definitions on robustness in the machine learning community. And here we are focusing on this probabilistic robustness definition, like in this equation 2. So this says, given a small region eta and a given label y, if I randomly select a data point from this region eta according to how the data point distributed in that region, what's the probability that this data point will be labeled as y? And now I will try to explain technically what exactly our reliability assessment model doing. Because of the time, I'm omitting some very important modeling details. So please refer to our paper for that. But essentially, we have 4 major steps in our modeling. First, we partition the whole input space into small cells, and the rule to decide the cell size is we try to make sure that the cell size is smaller than this R separation distance, which is essentially a property that first observed in this newspaper last year. And this property says intuitively, in the real world, for any two data points with different labels, there should be a minimum distance and denoted as R. So based on this rule of doing partition, we can confidently assume that all the data points inside a single cell has a single ground truth label. And this ground truth label will be used in our later steps. And in step 2, we try to approximate the operational profile. And we notice this problem is actually equals to the estimation of a probability density function over the whole input domain, given some operational data set. And we in paper we use this well-established KDE method. And you can see in this animation, this is the approximated OP when there are more and more operational data comes in. And in step 3, we invoke some third-party robustness estimators like this too. We try to evaluate the cell robustness to the ground truth label determined in step 1. Okay, and finally, we kind of assemble all the individual estimates we obtained from step 2 and 3 to get a reliability claim. So that is essentially we rewrite the definition of PMI at the cell-wise level, like this equation 4, which is a sum of product of the cell ice operator profile and the cell ice and robustness. And we can derive the mean and the variance of PMI given the mean and the values of individual estimates on NAPI and OPI, which are the cell-wise estimates for cell I, right? Okay, so in the paper, we did experiments on 5 data sites, and 3 of them are synthesized low-dimensional data sites, and 2 of them are high-dimensional image data sites. I missed the separation, right? And for each experiment, we compare between the testing accuracy and average cell robustness and our reliability results to have insights on those 3 different perspectives. And inevitably, indeed, we are facing some scalability issues when we are dealing with high-dimensional data like images. And we proposed some preliminary and compromise solutions in the paper that's something like instead of doing partition in the input pixel space, we do partition in the lightened feature space. And we also, instead of evaluating all cells, we only select top K cells, and depends on the budget. And the price we paid is we have more uncertainties in the reliability claims. And also we will keep looking for more efficient, more scalable KDE and robustness estimators in our future work. Right? In the paper, we also did quite extensive discussions on the 6 assumptions in our modeling. Because of time, I cannot go through all of them, but I would like to highlight 5 inherent difficulties of assessing deep learning reliability that are reviewed by our models. First is how can we accurately approximate the operational profile in a potentially very high dimensional input space with relatively sparse data. Second is about how can we build a accurate testing oracle, like leveraging the existing human labeled data in the training data set. Third is about what's the conditional OP inside a very small cell or very small region. That seems quite challenging. And then we need to efficiently evaluate the robustness of a very small region in the input space. And given normally the adversarial examples are real in ones, right? And in practice, for sure, we cannot evaluate all the cells, only maybe a small fraction of all the cells. So in this case, how can we build a efficient sampling method with unbiased estimators and better with some informed uncertainty, right? So to conclude, I would like to use this conceptualized equation, which says deep learning reliability should be a product of the generalizability and robustness. Intuitively, this says when we try to assess the reliability of a deep learning software, we need to not only consider how well it is generalized to a new data according to the feature occurrence profile, but also we need to think about how good the local robustness is around that new data, right? And we believe our reliability assessment model advances in this research direction because it seems like the first one to consider this OP information and the robustness evidence. And yes, because of this scalability issues is inevitable, we also propose some solutions for that. Last but not least, our model also discovered some inherent difficulties when doing deep learning reliability assessment. So yes, so thank you for your attention, and I'm happy to answer questions. And also, I would like to mention our ongoing project called Solitude, in which we are developing a better version of this reliability assessment model. We're also trying to build probabilistic safety arguments based on this model. And you can see we are also doing a case study based on a simulated autonomous underwater vehicle, like this animation. Yeah, that's it. That's it from me. Thank you. Thank you very much.
All right, thank you, Xinyu, for the presentation. So we're probably not able to take any questions. So we will leave the questions to the later session. Okay. So Romy, are you?
Yes,
yes, good.
I'm here. Can you see my screen?
Yes, yes, go ahead, please.
So thank you for the invitation. So I'll be talking about towards robust perception using topological invariance. This is joint work with Feng Liu and Pei Ke at the Huawei Munich Research Center. So the basic contribution of this paper is to import some new ideas in an emerging field called topological data analysis. In particular, we use the tool called persistent homology, and we experiment with it to see if it's how effective it is in problems in the field of robustness against perturbations and distributional shifts. And for our experiments, we take the task of semantic segmentation and we apply it to driving scene data, and we use a baseline unit model. So before going to the details, so some mathematics first. So algebraic topology is a old field in mathematics where you study geometric spaces up to topology. Topology is some very fundamental geometric feature of spaces. The study was initiated during the study of solutions of things like partial differential equations, and it's you can think of it as an extension from calculus to differential geometry to topology. And what algebraic topologists do is come up with algorithms that are not algorithms, come up with invariants for topological spaces. So the oldest such invariant was discovered by Poincaré a long time ago, more than 100 years ago. It's called the since then the subject has developed tremendously, and more sophisticated invariants have been coming up. The goal being to come up with invariants which can tell one shape from another. These are just shapes in any kind, embedded in any kind of high dimensional space. And then there is also a field called computational algebraic topology, where you would like to write algorithms to compute these invariants. And here, mostly the shapes are represented as some things called simplicial complexes, which are, you can think of them as a high dimensional version of graphs. So there's this new field called topological data analysis, which was initiated by Gunnar Carlson, a mathematician at Stanford, with the aim of importing some of these ideas to data analysis. In other words, you would like to understand the shape of data. So how would you import some of these invariants that are existing in algebraic topology to compute something like the shape of data. So here you could think of shape as consisting of something like connected components as being shape, or a number of loops as shape, and so on. And so the tool is called persistent homology. With the current versions of this tool, we could either feed it a point cloud data or some kind of image tensor. And what comes out is a diagram called a persistence diagram, which captures the topological information in that data. And this has been successfully applied in data science, and there are lots of academic communities progressing, taking this forward. Yes, and so the way we use it here is we take this tool and apply it to images, and the rationale for using this kind of tool is that it captures global information as opposed to local information, which usually CNNs capture. Although CNNs do capture some global information, but this is something handcrafted by mathematicians, and it's a very nice tool that we have, so why not use it? So the topological data analysis has some intersection with deep learning, again from ideas initiated by Gunnar Carlson, and it belongs to this. I mean, we can think of it as belonging to this field of geometric deep learning, where you think of data as having shape, and understanding the shape of data globally or locally to feed to when learning features. So here in our application, we are applying this to some kind of neural network, some encoder decoder neural network, which takes in images and gives out images or segments or whatever. Along with the training process, our idea is to introduce some topological loss, which computes the topological features from the output given by persistent homology, and feeds back the loss into the training process via back propagation. So one difficulty here is that this path going from images to this topological loss, which looks like this graph here, is not a path through linear algebra or calculus. So there is no notion of derivatives here, it's a path through combinatorics and algebra, and so there are ways around this problem. Again, we used some techniques developed by Gabriel from Carlson's lab to address this problem, and we use this to sort of append the topological loss function to some existing CNN. And the advantage of using persistent homology in problems using problems about images is basically it adds a new sort of invariance. If you think of CNNs being as a prior that encodes translation invariance, then persistent homology also adds other kinds of global invariances, which are difficult to write down, but they are there. It includes all kinds of topological invariances, and so in general includes any kind of Euclidean transformation as well. And they're also stable in some sense, so robustness is kind of built into this feature. You don't have to worry about it being robust. So there are mathematical theorems proving its robustness in the image space. So in our model, we take a usual unit, which is the top half of this diagram, and we take another unit and glue it alongside it with some shared weights in the middle, and we add some extra topological loss functions to the second output, and take them all together to do during the training process. And the idea, so the goal, the reason we applied it to image segmentation task is because the image segments have some very definitive topological features, like for instance, the cars are connected and so on. So, and the skies in one piece most of the times, and so you can in your hyperparameters for the persistent homology, you can sort of write them into your neural network. So there are a lot of hyperparameters that you can choose here. So what hyperparameters you choose depends on the combination of experiments and some prior knowledge. So here you can see some experimental evidence. If you can see my mouse, so here you can see in a usual unit here. So this human, this is the ground truth mask. It comes as a bunch of separate pieces, but here it more or less looks like it's getting to the right piece. So similarly here, the car here has some holes in it, but here the holes are filled up. So basically these are global topological features that are being preserved while training. Similarly here, all these people that are standing here don't come up. So this is the result of the unit, and they don't show up properly. Whereas in our coupled unit with topological loss, it seems to do the right kind of thing. Although this is not the right kind of reasoning you would apply to say your process is good, so you need some numbers, and here are some numbers. We also applied it for the distributional shift testing. We use the ACDC dataset, which is adversarial, driving data. It's like the cityscape dataset with all 4 different weather conditions. And yeah, I think I should stop here. Thank you. And there's a lot of details here, and the paper has some of the mathematical background in it, but more details can be found in the references. Thank you.
All right, thank you, Romy. Yeah, Lena, please do with your screen.
Sure, thank you. Can you all see my slides?
Yes, very good. Go on.
Thank you. So I'll start. I'd like to present our work on measuring ensemble diversity and its effects on model robustness. And before we start, let me just recap some of the basics of deep ensembles. In a deep ensemble, we have M members, and each ensemble member has the same model architecture, and it is trained on the same data set, just with random initialization. And then for classification at inference, each member outputs its predicted class probabilities. And then the ensemble output is the average of these probabilities. And the motivation for the topic of this paper stems from the good performance of deep ensembles and the fact that this is mostly explained by the diversity among ensemble members. In the literature, there are several metrics aiming to quantify this ensemble diversity, but are they also good indicators of ensemble robustness? So the main questions we asked were, first, to what extent can ensembles with the same training conditions differ in their performance and robustness? And second, are diversity metrics correlated with safety relevant metrics and therefore suitable for selecting members to form a more robust ensemble? Now let me introduce the diversity metrics we chose for our evaluation. First, we have disagreement, which is simply the fraction of samples for which 2 classifiers predict different labels. Then we have normalized disagreement, which is disagreement divided by 1 minus accuracy. And this aims to lessen the influence of just random predictions. Next, we have double fault measure, which is the fraction of samples for which both classifiers make a wrong prediction. And this indirectly also incorporates accuracy. And then we have output correlation, which is the pairwise correlation of the softmax outputs. And then these 4 metrics can be categorized into prediction-based diversity, which means that only the output is considered in the diversity. But then we also have cosine similarity, which can be categorized into weight-based diversity, which means that the parameters of the models are compared. And in that case, this is the cosine similarity between the model parameters of two classifiers. For evaluation, we used 3 types of architectures: a basic 4-layer convolution neural network, a mobile net, and a 34-layer ResNet. We trained those on Cypher10, Cynic10, and GTSLB. For each architecture and dataset, 20 models were trained, and then all possible ensembles of a combination of 5 out of the 20 trained networks were evaluated on in-distribution, corrupted, and out-of-distribution data. And for that, we used Cypher100 and SVHN. As evaluation metrics for ID and corrupted data, we used accuracy, accuracy at 1%, which is a kind of accuracy you get in practice when you exclude uncertain predictions below a certain threshold of probability. And in this case, accuracy at 1% is the remaining accuracy at the threshold where 1% of the samples are wrongly labeled as certain. And then we have the expected calibration error, and then something that we call the negative expected calibration error, which is the error that is only due to overconfidence. The metrics we use for out-of-distribution detection were the area under receiver operating characteristic and the false positive rate at 95% true positive rate. That means the fraction of out-of-distribution samples wrongly classified as ID at a threshold where 95% of ID samples are correctly classified as ID. Now let's take a look at the results on ID data. We first evaluate the variance of metrics in 5-member ensembles with the same training conditions. And we see that the accuracy may vary up to 2 percentage points, accuracy 1% up to 8, ECE up to 4 percentage points, and NEC has a very small variance. So we see that there's some potential for improvement by an aimed selection of ensemble members. So let's see how this correlates with the diversity metrics. And this is depicted here in this plot. It shows the correlation coefficients of the evaluation metrics with the diversity metrics. And here we focus on ResNets trained on Cynic10 at the top and GTSLB at the bottom. The evaluation metrics are plotted on the x-axis and the correlation coefficients on the y-axis. The diversity metrics are represented by different colors. This is where we also additionally define a baseline, which is the pairwise accuracy. And additionally, in this plot, the signs have been reversed where needed, such that any positive correlation indicates the more diverse the ensemble, the better it performs on this evaluation metric. So now we can say that baseline, double fault measure, and cosine similarity, which are depicted in blue, red, and brown, they correlate positively with accuracy at 1% and ECE. For NECE, we see almost no correlation, but as I said before, there's also very small variance to begin with. Disagreement and output correlation, they stand out as they sometimes correlate negatively, which means that the more diverse the ensemble, the worse it actually performs on this evaluation metric. And this is especially true for GTSLB, models trained on GTSLB. And next, just a short overview of our results on corrupted data. For that, we used 3 types of corruptions, namely brightness, contrast, and cutout. We saw that the variance of metrics was higher than on ID data, and the correlation with diversity metrics was generally weaker. But other than that, it's not drastically different to ID data. And finally, here are the results on our distribution data. And we again take a look at the variance metrics first. And what stands out is the large variance of FPR95 values on both out of distribution data sets with 25 and 43 percentage points, and also the AURC values on SVHN with 15 percentage points. So we can see that for those metrics, there's a large variation, and therefore the most potential benefit by name selection. So now let's see how this correlates with the diversity metrics. And we again see that the baseline, double fold measure, and cosine similarity mostly correlate positively with both evaluation metrics, but more for GCSRB than for CINIC 10. And then as an example of what these correlation coefficients could mean in practice, let's consider ResNet strained on GTSRB and then take the cosine similarity as our diversity metric. And then we can see that the most similar ensemble, namely with the highest cosine similarity, has a false positive rate of 15.8%, while the most diverse ensemble has a false positive rate of only 0.8%. So that's a difference of 15 percentage points in ensembles which were trained under the same conditions. And now to conclude, we saw that ensembles under the same conditions may vary significantly in performance and robustness metrics. And we saw that cosine similarity and double fold measure show a high correlation with the evaluation metrics, but rarely exceed the baseline of selecting this based on accuracy. And since we don't necessarily want ensemble members to be diverse in their output, but rather in their concepts and weights, future work should focus on new diversity metrics based on the specifics of DNNs, and ideally increase ensemble diversity and therefore robustness with the help of these metrics. And with that, I conclude my talk. Thanks for your attention, especially as we're approaching the end of today's workshop. And feel free to ask any questions in the following discussion or just email me or my colleagues. Thank you.
Thank you, Rena. So now let's thank all the three speakers of this session. I guess we now should move on to our debates panel. So Fabio and Jose, who will be able to help us in terms of the discussion. Are you around?
Yeah, hello.
Hello.
Hello, everyone.
Good,
Hello,
good.
hello.
Now I'm handing over to you. Okay.
Okay, Fabio, do you want to start? Or
Yeah, well, I can do it. In general, thanks everyone for the interesting talks and the presentations. Yeah, indeed, there were very interesting topics, and I have some questions, especially regarding to the first and third presentation. Maybe I can start with Seán Ó, maybe.
Yeah, good.
Yes, you mentioned at some point the curse of dimensionality. So I was wondering if you can elaborate better, because you mentioned there that we can work on the latent feature space, right? Yes, please.
Yeah. So as I mentioned in the presentation, the first step of our reliability assessment modeling is to partition the whole input pixel space into very small cells, right? And normally, because the rule of our way of doing partition is based on this R separation property, and that property gives us a very small distance, and so our number, so the number of our cells is quite large, believe me, and yes, so and practically we cannot, especially when there are high dimensional data, right? And there are so many number of cells. To give you a quick feeling, for the MNIST, we have something like 8 to the power of 25 times 25, something like that, right? So because of this high dimensionality, we cannot evaluate every single cell, and we can only select some of them with increased uncertainty. And also, even if we have given a single cell, we essentially invoke some third-party robustness estimators, and their approach is based on statistical methods. So again, when the adversarial examples in set SLs are real ones, it still takes quite long to do the sampling and to estimate, to have a unbiased estimate. Yeah, so that's why we have this scalability issue, right? And the way we try to solve it is we are thinking if we can utilize some low-dimensional latent space, right? But robustness by definition is defined on the input space, right? To the best of my knowledge, I don't know someone said the robustness in terms of a latent space. We always manipulate the input, the images like the pixels. I didn't see anyone manipulate some feature in the latent space. So in that paper, in our paper, we try to somehow learn the operating profile over the input space and mapping to features, the latent feature space, and learn another operational profile. And we again map it back to the input space to do the responsive verification and try to assemble them. Yes, it's kind of, I can't say it's neat, but yeah, I think that's the best we can do for now. Yeah.
In general, I think that's interesting because I don't know what you think, but maybe adding some constraints in the latent space can be helpful, as probably in the second talk was mainly focused, right? And yeah, another question maybe in general is, well, if we have this encoding to learn some kind of representation, yes, if we had perturbations to our input image, probably this image is going to be encoded in distribution, right? What do you think? So this another, yeah, if we, for example, if we get a variational encoder maybe, and we have an auto distribution sample, no matter what we pass there, it will always try to map this input to an in distribution setting into this sphere in the latent, high dimensional sphere in the latent space. And well, and yeah, so yeah, our next question regarding the last talk to Lina. I had a question related to the evaluation metrics, and I was wondering if it makes sense to consider perhaps other metrics, like since you're dealing with deep ensembles, and implicitly we can talk about uncertainty too. Do you think it makes sense to consider other metrics like negative log likelihood or Breyer score, for example, which are very well-known metrics in uncertainty, well, for in general for deep ensembles or whatever the method is?
Yes, sure. I mean, this was just like a first assessment of, and of course you can never evaluate robustness in all its forms. But sure, this would be interesting, and maybe also because we already talked about adversarial robustness, maybe this could also be one of the evaluation metrics. So of course this could be expanded to a lot more metrics if we'd like to investigate that.
Okay, thank you. And just one more question regarding the criteria you followed to choose the number of members for the ensembles. What was the criteria you followed to choose this number? Because I think it's 5, right? 5 members.
Just that from recent papers that adding more members to the ensemble doesn't necessarily increase the accuracy by that much, and then just practicality that we don't want to when we train 20 networks, we actually want some a lot of combinations that we can compare against. So yeah.
Okay, thank you.
Sure.
Yes. So yeah, I find the first and the third talk more closer to some of the things that I've been doing, and especially in terms of diversity related conditions. And so I'm more curious about the second one. So I'm going to ask a question about the second one. And I think that one of our challenges is trying to define types of variations, and of course you can start with the with variations on the input space, geometric variations there, And you notice that some of these variations they have nothing to do with, or even they are not perceptible by humans, some small variations. And some of these, for instance, can end up being noise or some other of these norms that are usually applied in adversarial attacks. Then we can go to the latent space and we can see that some other variations, they are a little bit more perceptual in the way that, so we can play with these variations and try to anticipate for them and get a little more robustness. And in this paper, I'm a little bit intrigued by these topological invariants and variations. So I think this is kind of a more powerful, in some ways of expressing these variations. And I think this is really nice. And for instance, this is, you can cover things such as rotations and symmetries using topology. I think this is great. My question is, even if these are examples where we see these alignments or something that that a human or even an animal would consider small variations such as a rotation, and you find the same thing with topology, maybe there's some other changes that are topologically minor, and we find them very strange from the point of view of human perception. And the related question is compositionality. For instance, if we have a dog with 5 legs instead of 4 legs, that's probably not accounted for by topology, or can this be covered as well? I'm of course, I lost many of the details about your use of topology, so that's why I'm curious about the potential of these approaches.
Okay, those are great questions, and I haven't thought about any of them. It's the first time I'm hearing those questions, so I don't have any good answers. But simply put, what topology does, it's if you take a grayscale image and think of it as a function on a unit square and draw its graph, then you can think of a convolution as a small patch which moves around that surface and tries to detect some local geometry, and topology are certain algebraic invariants that depend on global geometry, like number of peaks and number of valleys or other kinds of stuff that can be more complicated. That's just what it is. And now what I mean, this is just the application of that idea into image segmentation. It's difficult to extract meaning in the context of images very easily from what it does really. And even so for compositionality, which has some reasoning going on behind it, it's hard to say what topology has to do with that kind of compositionality.
But one question is whether you can, for instance, say that something topologically, something is a small variation, but it should be very relevant to the prediction or to the class or to the segmentation you're doing, and some others are not. So the question is, what of these variations are relevant to your problem, and which of them are irrelevant to your problem and you would like to be robust against? So that's a little bit my question. I don't know how easy it is or how useful this can shed light on this question.
So the classical topological invariants are discrete in nature. They are numbers. They are in integer numbers. And in topological data, because data analysis, you don't have numbers, but you have sort of things called barcodes. So the invariants now live in a continuous space, but there is a metric in this space of barcodes, a space of invariants, where you can do some kind of anomaly detection to discard the noisy ones. And that's what really topological data analysis does. It tells you what there is a metric in the space of these persistent homology diagrams, which tells you which ones are the relevant ones or the persistent ones, and which ones you should care about and which ones you should throw away. It's a sort of an analog version of the classically discrete topological invariants. in one of my slides, I had an image of a version of topological smoothing. So there I'm just turning the knob in this metric space to take an image from whatever its location is to some location where its topological noise is enhanced. So that kind of variation is, you can see from the slide that it makes a difference to the human eye, but it's not something you see in nature. I don't think so. It's not like the Gaussian smoothing or like you get in your phone apps. It's some other kind of smoothing. It's definitely detectable by human eye, but it's very un-image like. It takes you out of the image space in some sense. I don't know if I answered your question.
Yeah, no, I think it just goes in the direction of maybe, of course, I would need to read your paper because it's kind of and doing some of the background before understanding the whole of it. But I think that's really interesting as moving the conversation a little bit beyond some other more some simpler notions of variation sometimes, and of course that could also affect some of the metrics that perhaps paper 1 and paper 3 they're using. So I don't know, Fabio, maybe if there's some questions from the presenters to other presenters, or maybe if I think John has a question, so yeah, maybe John, you can.
Yeah, thanks, Jose. I'd like to go back to the first paper, which I'm really pleased to see somebody looking at the operational profile. Reliability is a joint distribution, not a property of a system. So I think that's really great. But as was acknowledged, it's really quite hard to model that distribution. What I wondered if you think, is there some way of overcoming some of those uncertainties by saying, hey, we can place a lower bound or an upper bound on the reliability. It's going to be no better than this, or it's going to be no worse than that. Because I think resolving all those difficulties is going to be extremely hard. But if we could actually make some bounding arguments, that might actually be very practical. And I just wondered if you thought that might be feasible. Sorry, a tough question, but it's really piqued my interest that it might be really practical in some really hard cases.
Yeah, it is a hard question, and I think.
Sorry.
No problem. That's good because this problem we actually calculated in our paper as a inherent difficulties for assessing the deep learning software reliability. Indeed. And I think currently in our ongoing project for this learning on the operation profile stuff, we are trying to combine some human expert knowledge into the learning of the operational profile. And we did notice some very interesting technical solutions here. Like I'm not sure if you heard of this thing like conditional VAE, variational encoder, right? So basically you can learn the features in some latent space, and you can manipulate some features, like you can make their mode data to smile, right? You can generate mode data with sunglasses, and we found that technique will allow us to actually embed some human knowledge to generate a operational profile in the future. I would say, sorry, not a operational data set in the future. So I hope I'm answering your question for this OP stuff. Yes.
Yeah, sure, you are. No, I mean that we should have a conversation offline. I think that's very, very interesting to combine the models with expert knowledge. Maybe the best way we have of actually getting some sensible estimate of reliability. So thanks. That's very interesting. We'll follow up when we can. Thanks.
Thank you, John. Thank you.
Mauricio, you have a raised hand.
Yeah, and can you hear me? Yeah, I was just wanted to check whether my first comment whether Xingyu saw my first comment where I was asking about your awareness of distribution aware testing that, some work that is going on. I think it started in Singapore. Now it's, people here at University of Virginia are, doing researching that topic. And how much are you aware? How the relationship that you see with the stuff that you're doing?
Sorry to say that I only aware one paper. I think that's the one you mentioned from Virginia, published in the ICSE last year, right?
Yeah, exactly.
Yes, I only read carefully about that one paper.
Yeah.
And I think in that paper, they try to say, validate test cases, right? Something like, depends on the distribution, they try to label the test cases they generate is validated or not validated. And they try to compare between coverage guided testing and whatever the deep learning testing method.
Yes.
And they claim their method can generate more valid test cases.
Yeah, and in theory, when they say validated, they mean actually test cases that are relevant to the operational profile.
Yes,
right?
yes, I believe. Yes, I believe so. Yes, yes, it's quite relevant, and I believe different community has different terminologies. Operational profile is more like software engineering, right? And where there are more machine learning stuff. So yeah, so quite relevant. And also you mentioned you are developing something similar. So I'm quite happy to have a read, have a more in detail discussion with you, with your group.
Yeah. Okay. Yeah. That'll be great.
Looking forward to it.
Okay, maybe we can continue with some questions because this is the last session, so you have to leave. You will probably do without our permission. So let's go for the next question. Michael, please.
Yes, I have a question to the last talk, was about the ensembles. And I think I see in the presentation that there was, let's say, very hard to beat the baseline approach that is used for comparing the other approaches. So my question on the author is there some idea why it's so hard to beat this baseline? Are there some fundamental problems, or maybe where the, let's say, the models not, let's say, saturated in their accuracy, so that the variance that is observed was more about, let's say, better and worse trained models? Or is this, let's say, a fundamental underlying problem, so that this approach have some problems looking on diversity?
Thank you. Great question. We haven't actually looked into it, but I think, of course, we saw that there's some variation in ensembles that were trained on the same conditions. So we see that alone this, well, if we then use the baseline, which is based on the accuracy, we can then just select the best model or the best ensemble. And what we were trying to do actually is evaluate all those ensemble diversity measures in how they actually, what their influence is on those evaluation metrics, and not really beating the accuracy or the baseline, but more like just looking at it and comparing it. And I think it just shows that accuracy is still like the number one metric we can look at. But I mean, for example, for out of distribution detection, we just simply used a threshold at the output probability. So when we have higher probabilities for the predicted class, which would be the case of the accuracy would be higher, then it's maybe a bit easier to select the threshold that is detecting out of distribution detection. But yeah, I mean, I think it would be interesting to test a bit more of those diversity measures, or maybe try some new ones to see if they maybe come close or even beat the accuracy one. Yeah.
Okay, thank you very much.
Okay, so I don't see. I had a connection here with the invited talk, but I don't see Tay Ann here. So Mauricio has another question, or maybe a raised hand that hasn't gone down.
I'm sorry. Yeah, I'm sorry to keep you a bit longer.
That's
One
fine.
question for Lena. I wonder if you were starting to glean sort of design decisions for the ensembles from the results. I mean, or is it still too early to talk about how that may influence how you design this ensemble systems?
Sure. I mean, from the 2 points that or the main points that we found was that there is a large variance, and I think this shows that when we want to use deep ensembles in safety critical applications, we should consider training more models that we actually need in our ensemble and carefully select the ensemble members. Since if we just train 5 models and use those for our ensemble, this might not be the best outcome we can get. And second, that simply selecting those members then based on accuracy might for now be good enough, or just that the ensemble diversity measures that are out there right now don't show any additional diversity that is needed for robustness. So yeah, I think these 2 main points.
Okay, thanks.
Sure.
Okay, so maybe